In this video session, we are going to see how the pressure transducer works for the biomedical instruments. Okay, so pressure transducer or a pressure sensor actually has a very important role in the biomedical domain. Okay, the human body is actually full of so many types of organs, bones, joints, muscles, so many types of different kinds of combinations are present in the human body. So many parts are there. Okay, now every every part of the human body, you can say, whether it is organs, okay, whether it is tissues, it is bones, joint bones, muscles, every part, it has its own characteristics. It has its own volume, some pressure, some structure. Okay, so basically, the human body, or you can say a living organism's structure, is actually full of so many parts, and every part has its own pressure. Okay, every part, when it is functioning, it has either it is exerting on the other parts, or it is being exerted by the other parts. So somewhere every part has its own pressure coming into picture. Okay, so either it might be a normal operating the pressure is generated, or maybe due to some illness there is some dynamic change going on in the physiological changes taking place in the body, or in that particular body part, that can create certain dynamic changes in the pressure. Might be due to illness, might be due to some disease, okay, some unwanted tissues, some growth, so anything like that. So what I mean to say is that human body is full of so many parts, and every part, when it is functioning, whether its own normal functioning or there is some abnormal functioning due to illness, it has its own pressures. And all those pressures, when we measure, they can actually give you a very valuable information about human body. It can tell you whether the functioning is normal or not. If the functioning, if there are certain discrepancies in the reading, it might be actually an indication of some illness. It might be onset of some disease. So all these body parts, their pressure measurement is actually very important. So in the figure, you can see that human body can actually be divided into so many types of pressures. We have brain pressure. That is called intracranial pressure. If it is eyes, we have intraocular pressure. Then for heart and vessels, we have blood pressure. So many types of pressures are there, which are all the time functioning inside our human body, and all that together is actually making a human body function like we see it or we are experiencing it. So pressure transducer in biomedical domain is a very important uh, uh, component. And most importantly, we need the component or the sensor to be very accurate, and at the same time we need the structure to be such that you can place it at a very precise location in human body. If it has to be placed at some particular nerve, so it has to be so small and it's so accurate that it can actually be placed at that particular location. So within human body, these pressure sensors, they are very specially designed pressure sensors, which can be used either inside the human body or outside the human body to measure so many different types of pressures that are operating all the time within the body, right? So the requirement of a particular pressure sensor technology is dependent upon the area of interest. So which particular part you want to measure the pressure for, place of measurement, whether it is a tissue, whether it is muscle, whether it is bone, and the method for which the sensor is to be employed, whether it is a single point measurement or you want a long term observation. Okay, or it maybe, like for example, if a person is in coma or the person has cancer. So depending upon these three factors, we actually select, or you can say we design a pressure transducer for a particular biomedical application, right? So basically there are two most common principles which are usually applied in some form or the other in the biomedical applications. One is the classical strain gauge transducer, and second one is the diaphragm displacement sensor. So strain gauge we have studied earlier also, but we'll be quickly going through it. So strain gauge is basically, we have studied that these are metallic wires. You can see the chip in the figure. This kind of a geometry is made, and it is a device which actually, undergoes a change in geometry, and as a result of that, the resistance, electrical resistance of the device changes, and it gives you a corresponding change in the voltage. Okay, so wherever the strain gauge is placed, okay, whenever there is a change in pressure basically, change in pressure or change in force, you can say that it will, either the surface will be elongated, or it might get stretched. So along with that surface, your strain gauge also gets stretched. So there is a change in geometry in the strain gauge also. Okay, so that change in geometry actually gives rise to a change in electrical resistance, and then that electrical resistance change will actually give you a fluctuation in the voltage. So we have already, in the earlier lectures, we have studied what actually strain gauge transducers are, just to brush up. And the gauge factor, you all know, or the sensitivity of the strain gauge is given by the change ratio of change in resistance with respect to change in length. Okay, so this is one of the fundamentals which we can use, because this is also very, you can fabricate a strain gauge chip of a very micro level, and you can implant it at various places of human body. And when those changes are taking place in pressure, the strain gauge actually experiences some force, it experiences some strain, and the geometry changes, giving rise to change in electrical resistances. Okay. And the second important fundamental is, diaphragm displacement sensors. Now, this one is actually very, very important when it comes to measuring the internal pressures. If for any particular reason you have to implant a pressure sensor inside, if you have to put a cut in the skin and you have to plant a sensor inside, usually we use the diaphragm displacement sensors. Okay, so diaphragm displacement sensors, they are based on micro electromechanical systems technology, in which the sensors, they have a bendable flat surface on a sealed cavity. The diaphragm, it bends according to the change of pressure, and can be capacitance based or based on piezoelectric transducer. Now you see in the figure, this is what actually the tip of the sensor looks like. Or you can, if you have to understand the fundamental of diaphragm display sensors, we'll understand with the help of this figure. Now in this figure, the on the three sides, which you see a shaded kind of, you can see this particular shaded kind of horseshoe structure. This is a sealed cavity. This whole thing is a sealed cavity, and this particular, you can see over here, labeled as dia, this is actually the diaphragm film. Now diaphragm film is actually a bendable structure, on which, when there is some pressure applied, it bends. Okay, that is diaphragm. So this particular one in this particular rectangular cavity that you see, three sides are sealed, and on the fourth side we have a bendable structure, or you can say we have a diaphragm over here. Now in this, diaphragm is fixed from two ends, and in between it is flexible to move, right? So whenever there is some pressure applied on this diaphragm, due to some external activity, whenever there is a pressure applied on this diaphragm, since it is fixed from the two ends, it will bend. So it will result into a curved structure, as you can see. Now when it results into a curved structure, whatever fluid or air, incompressible, which was inside the sealed cavity, now the pressure that will be exerted to these three walls will actually change. Okay, because you see the cavity, now the shape of the cavity has changed. So whatever liquid or whatever air, fluid is there inside, jo uska pressure that it is applying on the walls, now it will change. That pressure change will actually be corresponding to the delta P, or the pressure change that has been applied to the diaphragm. Okay, this pressure change actually we can measure. You can measure it with the help of a capacitive transducer. You can measure it with the help of a piezoelectric transducer. But the change in pressure which is applied on the diaphragm, due to the pressure that is applied on the diaphragm can actually be converted into an electrical quantity. So you have a sealed cavity. It is fixed from three sides. The fourth side has a diaphragm, which is actually a bendable structure. When there is some pressure applied onto the diaphragm it bends and the structure of this sealed cavity changes. Okay, so this now change can actually be measured in terms of an electrical quantity, either with the help of a capacitance based transducer or with the help of a piezoelectric transducer. Right here you can see that you know a little bit clear it will be that the how the diaphragm is actually bending. Delta P is the pressure that is applied. Delta V is the change in volume that has occurred of this cavity now. Okay, earlier it was having inside the pressure was P naught and volume was V naught. Okay, now what happens, the volume of this cavity actually changes because delta V volume has come, has been eliminated from that. The diaphragm has been pushed inside, so the inner volume of the cavity has reduced. So when the volume has reduced, the pressure that is being exerted on the other three walls will actually increase. Okay, this pressure, how we are going to measure, we'll see. So for example, if at all I want to measure it with the help of a capacitive fundamental, if you see in this particular figure, this assembly consists of an airtight housing in which the metallic diaphragm is placed. At the inner side, there's a fixed plate. Okay, in between the diaphragm and the fixed plate, the dielectric medium is placed. When you apply pressure on the diaphragm, it moves towards the fixed plate, resulting in the change in capacitance. This capacitance is calibrated into voltage proportional to the applied pressure. Now, if you remember, when we were studying capacitive transducer, we had seen that when the two plates they move relative to each other, either the distance between the two is changing or the overlapping area is changing, then we can say that the capacitance changes. So same thing is over here. When you can see over here the dotted line, this was the original position of the diaphragm. Okay, so when at that particular time the distance between the two was different. This over here you can see this is the fixed plate. This dotted line is the original position of the diaphragm. So at that particular time, the capacitance would be something else. When we apply pressure to this diaphragm, the diaphragm, since it is fixed from two sides, it bends. And now you can see that in the center, fixed plate and the diaphragm, the distance between the two has reduced. Okay, so according to the capacitance formula, the correspondence change will be introduced in the capacitance, right? So the capacitance change is further calibrated into a voltage change, which is directly proportional to the applied pressure. Similarly, what you can do is instead of putting a capacitance structure over here, another type of example could be that just below the diaphragm, you can place a piezoelectric crystal. So what will happen when you apply the pressure on the diaphragm bends, and that bending will actually, introduce a bending on the piezoelectric crystal, and the piezoelectric crystal will give you a corresponding voltage signal. So diaphragm sensitive sensor or a diaphragm based sensor is actually very, very important when we are measuring the pressures, mostly when you have to measure from within the human body. Now, another important point over here is that if at all I have to measure or I have to implant the sensor or I have to measure the pressure of some particular point inside the human body, suppose it has to be inside the heart at some valve. I want to measure the movement or the pressure inside a valve and I want to plant a sensor over there. Now, all these, sensors that we are using, either it is made up of some metal or something. So sometimes what happens is we wish to avoid actually planting that electronic thing inside the human body. Okay, and moreover, it is very difficult to reach out to that particular point. Sometimes it is so small, so fine that it becomes difficult for the that sensor to actually reach that exact point. So at that particular point, what comes to our use is catheter tip based pressure transducer. Now you all must have heard what catheter is. Catheter is actually a very thin tube which is made from a medical grade material, and it can be used for a variety of applications. Basically, it comes in various sizes, and this is a very small, very thin device which can be inserted into a human body either to treat the disease or for some surgical procedures. Okay, by modifying the material or adjusting the way the catheters are manufactured, it is possible to tailor catheters for cardiovascular, urological, gastrointestinal, neurovascular, ophthalmic applications. So, catheter is nothing but a tube, a very, very thin tube, which is made up of a material which is medically proven, which is not, infectious, which is safe for human body, and it is of such a size that you can actually insert it inside the veins, the arteries, the muscles of human body. And depending upon which particular part you want to insert, whether it is heart or whether it is your kidneys, whether it is your neuro system, you can design the catheters in various sizes. Okay, and but the ultimately the task of the catheter is actually that it should be so fine that it can be inserted inside the particular vein or a particular artery. So this catheter tube now we are going to use to measure the pressure inside. Now what we do is we take a catheter tube, okay, we fill it with incompressible medium, okay, and now it is sealed from both the sides. It is incompressible. Now incompressible medium means the medium, the fluid, either it could be water or it could be some saline solution whose volume does not change. Okay, so this is a very, very important thing, that the medium that you fill inside the catheter tube has to be incompressible medium. So what we do is we have a catheter tube which is sealed from both the sides, and inside it is completely filled with a incompressible medium. Right? Now what happens is at one tip, now if you see in the figure, at one end of the catheter tip there is a small structure, diaphragm kind of structure. एक छोटी सी cavity बना के उसमें एक पतला सा diaphragm film लगाया हुआ है. Okay, and the other end of the catheter tube is actually connected to some pressure sensor. Either it could be capacitive or either it could be a piezoelectric sensor. Now what happens is when you place this catheter tip on, suppose I want to measure the pressure changes occurring in some valve in the heart. So what I do is this catheter tip I place at exactly at the surface of that particular valve. Now when the heart is going to pump the blood, the valve, the walls of that particular valve will move up and down due to the force of that blood. Okay, that particular force will be transferred to the diaphragm. जैसे जैसे आपके वॉल्व की जो सरफेस है या वॉल है वो it will move up and down. Correspondingly the diaphragm will also move up and down, and the diaphragm will be in a curved shape like you can see in this particular figure. Now when you are making the diaphragm curved, it is just like pushing the diaphragm from one side. Since it is incompressible liquid inside, at the other end there will be some bulging out of the tube, right? It is something like if you have you take a balloon, you fill it with water completely. If you fill it with water, if you try to squeeze it from one side, other side it bulges out. So same thing is happening over here. From one end, if the pressure is exerted inwards, the diaphragm is moved inwards inside the catheter, the pressure gets transmitted through this incompressible medium to the other end, and the other end valve of the catheter bulges out and exerts the same pressure on the sensor, the piezoelectric sensor or the capacitive sensor that is placed on the other end. Okay, so from one end, whatever pressure you have exerted on the diaphragm will exert the same pressure on the incompressible medium, and the incompressible medium will exert the same pressure to the opposite or the other end of the catheter tube, and that pressure will be transferred to the piezoelectric crystal attached over here, and that piezoelectric crystal will take that pressure and create or generate a voltage signal. Okay, so like this, we can actually use a catheter based pressure transducer for having a very accurate measurement from within the body. Okay, so you can see this is what actually it is based upon. The operating principle is something like this. If you press from one side, and this closed cavity is filled with a incompressible liquid, the other side will bulge out. Same thing is happening with the help of catheters. From one side, if I press, you can consider this as a first side is one end of the catheter, and the other this piston 2 is actually the other end of the catheter. So from one side, if the wall of any heart valve exerts a pressure, this goes down, the other end will bulge out, it will be rising. So this particular, the other end, if I attach over here, like in this example, if you see, if it at this piston 2, if I attach suppose a piezoelectric crystal over here, what will happen when I exert force from here? The same force is exerted outwards from this side, and the piezoelectric crystal will capture that force and give you a voltage signal, right? So overall, you can see this is how it looks like. You can see over here, the first figure, if you see, this is a big catheter, and at the end, this is what it looks like. This grayish structure, you can see that the grayish structure is the diaphragm over here. And in this figure, you can see that on this particular diaphragm, to and from, whenever the pressure will be applied, it will take curves. Sometimes it might get swollen up, sometimes it might get curved inside. So this is a diaphragm over here. Now when this particular, from here you can see in the third figure, from this site of measurement over here, when the pressure changes take place, the diaphragm, it bends. When it is bending over here, this incompressible liquid inside this particular catheter is transferring the pressure from this particular site of measurement to the sensor that is attached over here. This might be a strain gauge, this might be a piezoelectric crystal, this might be a capacitive transducer. Over here we can have a sensor. So this pressure will actually get attached over here. Electric voltage signal will be generated. It will be sent to the amplifier. It will be suitably amplified, and then at a recording display, you can see whatever the output is given to you, or you can see how the pressure variations are actually taking place inside the body. Okay, so you have seen that pressure is a very, very vital parameter of human body. Pressure transducers are very important. And in general, we have either strain gauges or we have diaphragm based methods. Strain gauges are mostly used at the outer surface wherever we have to measure the outer surface pressures. Okay, there you can use strain gauges. And whenever you have to have an intravenous, where inside you have to implant at some site, you want to measure the pressures, there we use the diaphragm displacement method with the help of a catheter tube. And catheter tube actually is a method of transmitting that particular pressure from the site of measurement to the sensor, because sensor cannot go inside the body. So we are bringing that pressure out so that it can reach the sensor. The sensor will correspondingly generate a voltage signal, and that will be given to your display device. So that is how actually the catheter tip pressure transducers, they work.